Okay, can all of you see this OneNote page?
Yes, sir.
Yes.
Okay, so we are doing what is called the transformation of a variable. Okay, I think the name is uniform transformation, and you are doing the continuous random. Okay, someone's mic is on, and please off it. Dizipia Yalam, your mic is on. Please off it. So we are doing the continuous transformation. And in transformation, we studied already that discrete random variables. Now we will study the continuous. Now we were studying the continuous random variable. Now, so we started with some example, then we'll see some theorem which will make our work easier. So the theorem is y is equal to x squared, right? This theorem we're doing. So this is the distribution function of the random variable y. So this is by definition y is equal to y. So this is by definition p. What is capital Y? X squared is equal to y. This is p minus root y is equal to x is equal to root y. Okay, and so this is, we see that we have seen this before. This is f root y minus f root minus root y. So this is from where? This is like p a is equal to x is equal to b is equal to fb minus fa. This thing we proved. This thing we proved before. So fyy, the distribution function is f root y minus f root minus of f root minus x. So this is x, the distribution function of x. Okay, so now from distribution function, how will we get the density function? Can anyone tell me? Okay, what is the relation between the distribution function and the density function? Is there anyone who can tell me? Okay, first when we define density function for continuous variable to be function is a function such that if non-negative and this integration minus infinity to infinity fx dx equal to 1. Then we define density function from the distribution function from the density function by this integration minus infinity to x fy dy. So f of x is equal to f minus f x prime x, f suffix x prime derivative at the point x. So this happens. There are some conditions. So this capital F function has to be continuous everywhere and differentiable except at a finitely many points. So it's differentiable at everywhere except at finitely many points. Then we can do this. Okay, you can just take the differentiation and you can get back the density function. All these things you understand that we did in the last class or before that. So fx is equal to the density function is the derivative of the distribution function. So if we take this density function of with respect to the random variable y, that will be d dy of f x root y minus f x minus of root y. So this is 1 by 2 root y if x prime root y minus if x prime root y. Okay. Any question here? So this is actually some variable change. Okay, this is actually, you can see. So this is where, so this thing you can write as d dx if x, okay. Okay, I'm sorry, this is not, we have to take the derivative of both sides. So this will be variable of y, right? Yeah, so this is variable of y. Just 1 second.
एफ डैश प्लस होगा ना वो मतलब प्लस एफ डैश
कौन सा वाला? Which one?
सेकंड में 1/2 रूट
And
पाई
this
होल
is plus, right? This is plus, right? Okay.
इंटू
Yeah. Just give me 1 minute. Wait. So, just name of change of name, like as it is. Okay, so this will be this will be what, right, this way. So this root of minus y if x root y, then d root y by dy. Okay, this thing we know, you know. So again, d of d root over minus y. You want plus here, and minus of d of d. So you just consider this root over minus of root over y as some other variable. You can write this as z. So this is if x over minus y into d minus y by dy. And if you do this, then you will get this. Okay. So this is, so that will be same as this. Just you will do some variable, change of variable. So we will get ultimately 1 by root over 2 root y if x over y plus f of x minus root over y. And this is true if y greater than 0, because the variable is, you see that this is the random variable y is equal to x squared. So we need y greater than 0 and 0 otherwise. So this is not the rigorous proof, but okay, we can prove this rigorously. Okay, so this is what we have done, is not a rigorous proof. Again, I'm telling. So this is the way. Means we can just take the differentiation and take the differentiation, do the change of variables things, and you will get this is the density function of y. Because you know the density function of x, from this you can get the density function of y. This is the density function of y. But this is not the rigorous way of proving this. But we can prove this rigorously, which I have omitted here. So now one particular type of density function or distribution function we will introduce. So these are some of the density function or distribution functions we are giving as examples while we study all these things, density, distribution, data. Today we'll start this expectation movement. For during this we'll study some of the examples, but there are some special examples which are called special distribution functions, which we'll study after finishing this up to Chebyshev's inequality. After that, we'll study the special type of distribution or special examples of density distribution functions. So let A less than B, B2. So this uniform density function you have seen before. I'll just give the definition, then you will see. B2 real numbers the uniform density on the interval a comma b on the interval a comma b is the density f defined by so these are density function for these are continuous density function. Okay? Density function f defined by fx is equal to 1 by b minus a for a less equal to x less than b and 0 elsewhere. First, you tell me why is this a density function? Anyone tell me why is this a density function? Gattipati Lassia, you tell me why is this a density function? You are not here. Ushab Kumar Patel. There are 142 people and one is responding to me. Okay, your mic is not working. That's good. So Gattipati is at least you are here. So okay, you cannot tell me that. Okay, fine. Ankit Kumar, are you here? Ankit Kumar. Argho Sarkar.
Yes, sir.
Good. So you tell me why is this a density function? This function I have defined 1 by b minus a less equal to x less equal to b. Why is this a density function? So what is the definition of density function? For continuous, see, we can define distribution function for any random variable. Okay, but for any random variable, we can't define the density function. We can define the density function only for two cases: discrete and continuous. Though these are the two major examples, all the major examples are either discrete or continuous. But for any random variable, we cannot define density function. So for continuous density function, continuous random variable, how we define the density function? Anyone tell me? Ankit, you tell me. Miss Ankit, right? No, Argo Sarkar, you tell me. What is the definition of density function? So density function means f is greater or equal to 0 and the integration from minus infinity to infinity fx dx has to be 1. Here this is a to b dx by b minus a, and which is b minus a by b minus a is equal to 1. So this is a density function. And how will you get the distribution function from here? Fx is by definition minus infinity to x fx dx. This is minus infinity to x 1 by b minus a dx, and which is 0 if x less than a, x minus a by b minus a if a less than x less than b, and 1 if x greater than b. Okay. Now this particular example we have seen before. This fx, we saw that in the example in the previous class we did. So here we studied this example. Fx is equal to 0 if x less than 0, x square by r square if 0 is equal to x is equal to r, and 1. So is this a uniform density function? Anyone tell me? Is this a distribution function which comes from a uniform density function? So here this x squared thing is there, so this is not uniform density. Okay. From distribution function. But after that, you remember what is this thing? So there is a radius disk of radius r, and you are picking a point randomly from that disk. So that has this distribution function. Okay, for that. So you are taking a point randomly from that disk of radius r, and the variable is here the distance of that point what you have chosen from the origin. So this is not a uniform density function because this x square part is there. But if we take y is equal to x square, then we have seen if y equal to 0, if y less than 0, y by r square if 0 is equal to y less equal to r square, and 1 if y greater equal to r square. So this is uniform density. Uniform distribution function. And for discrete case also we have studied the uniform density function. Like if there are odd number of points are there, you are choosing any point randomly. So each has the same probability 1 by r. That is uniform density function for discrete. Here this is the uniform density function for continuous variable.
Sir,
Any
can you
question?
repeat the definition again?
Which one?
Of uniform distribution.
Shall I repeat the definition?
Yes, sir.
So this is the definition function. Just this is the definition function. So A less equal to B, then two real numbers. The uniform density on A comma B is a density function f, which is defined by fx is equal to 1 by b minus a if A less equal to x less equal to b and 0 elsewhere. And from there we can get, using this definition, minus integration minus infinity to x fx dx, you get the distribution function, which is this. 0 if x less than 1, x minus a upon b minus a if a is equal to x is equal to b, and 1 if a is greater than b. Is this okay?
Yes, sir.
So in the previous examples, so what we saw, so this example, so means we are going to now state one result. So before that, y is equal to x square was the thing, and which is 1 to 1 on 0 comma r, right? And outside 0 comma r and outside 0 comma r square, which is just 0 comma r its square, the density function of f is 0. Similar cases happen for the next theorem, which we'll state now. So let phi be a differentiable strictly, let phi be a differentiable strictly increasing or decreasing. It will be either strictly increasing or strictly decreasing. Function on an interval I let phi I denote the range of phi and phi inverse the inverse function to phi. Let x be a continuous random variable having density f. Having density f, it's not x. Let x be a continuous random variable having density function if which is 0 such that if x equal to 0 for all x doesn't belongs to I. So this is the function, this is the interval I on which the function phi is differentiable in strictly increasing or decreasing function, outside which we don't have any control. And on this, the image of, okay, this is not, okay, on this f, on this on the outside this interval I, this the density function of f is 0, then so this is exactly the previous case, then f y is equal to phi of x phi of x has density g given by gy equal to 0 for all y doesn't belongs to phi of I, and gy equal to f of phi inverse of y mod of d dy phi inverse of y for all y belongs to phi I. Because on this function, on this interval I, this function is see 1 to 1 because it is strictly increasing or decreasing. So the function phi is 1 to 1. So we can talk about the inverse function, which is phi inverse. This is an interval and this map is either strictly increasing or decreasing. So its image is also phi I, which is an interval. And on this function phi inverse is defined. So this is the way we can give gy. We can get gy. Okay. So gy is the density function of y. This is the way we can get gy. And we write this in this form. We write the previous thing in the form. So this is the easier way for us to understand. Gy is equal to f of x mod of dx dy for y belongs to phi I, and x is equal to phi inverse of. Okay, so in the previous example, actually we are using this. So you understand the previous example that this is the 0 comma y. So which is not only 1 to 1, is strictly increasing. Is y is equal to x squared is strictly increasing on 0 comma y squared, 0 comma r, 0 comma r, and outside 0 comma r, I'm sorry, this is not r square, this is outside 0 comma r. This density function of x is 0. So outside this interval, the density function is 0. Okay, and on this same interval, this transformation y is equal to x square, or any transformation we can take phi x, that has to be differentiable and strictly increasing or decreasing function. Then we can find the density function of y in this form. So y is another random variable. So for which you can also find the density function by doing all these computations. But already for x we have that density function, and it will be many times it will be easier to directly find the density function of y from the density function of x, and for that we have this formula. Any question? Proof is omitted. So in many books, or I think in all the books, the proof is given. If you want, you can see from there. I don't think I have that much time to give the proof. Okay, any questions you have? Okay, one example. Let x be uniformly distributed on 0, 1. Find the density of y is equal to minus lambda inverse log 1 minus x for lambda greater than 0. Okay, so you tell me, so the density of x, the f of x is 0 outside 0 comma 1, and on this interval 0 comma 1, how this transformation y behaves? You tell me that. Anyone? On 0 comma 1, y is equal to minus lambda inverse log 1 minus x is strictly differentiable and strictly increasing. Am I right? So we have to find the density function of y. So how will we know that gy is equal to 0 for all y doesn't belongs to phi of 0 comma 1. Here phi of x is equal to minus lambda inverse log 1 minus 6. Okay, and this is equal to f of, just we are using the previous theorem. You see that this thing is there, this thing. We're just using that. F of phi inverse y into mod d dy phi inverse of y. Now x belongs to 0 comma 1 implies y belongs to, I think, 0 comma infinity. Yeah, y belongs to 0 comma infinity. So, and what is phi inverse of y? Phi inverse of y is equal to x, right? That means um, so y is equal to minus lambda inverse log 1 minus x. So this gives lambda y minus log 1 minus x. So this gives e power minus lambda y 1 minus x. This gives x is equal to 1 minus e power minus lambda y. Okay, so phi inverse of y is equal to 1 minus e power minus lambda y. So ddy of phi inverse of y is equal to lambda e power minus lambda y. Okay, so what was gy? Gy was f of phi inverse of y mod ddy and phi inverse of y. This is when y belongs to phi of 0 comma 1, that is equal to 0 comma infinity, and this is so this will be f of phi inverse of y. So what is f? F is just 1. So this is just 1, and this will be lambda e power minus lambda y. Okay, so this gy function is nothing but lambda e power minus lambda y for y belongs to 0 comma infinity and 0 elsewhere. So this is called, so we'll see all these things. These are the some special distribution function or special density functions which we'll study in details later. So this is called exponential density with parameter lambda. Okay, any questions? No questions you have? Is there anyone who is listening? Anyone listening?
Yes, sir.
Yes, sir. Yes.
Okay, fine.
Yes, sir.
Okay, fine. So any questions do you have? Whichever we have discussed today, do you have any questions? Okay, next example we'll see. Another example. So let x be a random variable with an exponential density with, so the density function is exponential with parameter lambda. Find the density of y equal to x power 1 by beta, where beta not equal to 0. So we have to find the density of this new transformation, this new variable, which is the transformation of x defined by x power 1 by lambda. So we just use the previous theorem again here. So in this case, we know that fx, the density function, is lambda e power minus lambda x, where x belongs to 0 comma infinity and 0 elsewhere. So here phi x is equal to x power 1 by beta, which is one strictly increasing, I hope, strictly increasing or decreasing, depends upon whether beta is greater than 0 or less than 0, decreasing on 0 comma infinity, or which the function is non-zero, the density function is non-zero, on that this transformation is either strictly increasing or decreasing, depending on beta is greater than 0 or less than 0. So here y is equal to x power 1 by beta. So y power beta is x. So phi inverse of y is equal to y power beta. So ddy of phi inverse of y is equal to beta y power beta minus 1. So gy is f of phi inverse of y mod ddy of phi inverse of 1 if y belongs to phi of 0 comma infinity and 0 elsewhere. So this is equal to, what is f of phi inverse of y? F of phi inverse of y is equal to so we have to put this lambda e power minus lambda x. Okay, so here phi inverse of y is equal to x. So lambda e power minus lambda x, and this is, from this we will get beta y power beta minus 1 for y belongs to 0 comma infinity again and 0 elsewhere. And this is now for x. So y is equal to x power 1 by beta. So x is equal to y power beta. So lambda e power minus lambda y power beta into beta y power beta minus 1 if y greater than 0 and 0 elsewhere. I hope I have written correctly. Okay, this is with mod beta. Mod beta lambda 20 minus 1 right. So is this okay? So this is another example of this g function. So this function x y is equal to x power 1 by beta is given. This is a transformation of the given function of a given random variable x, whose density function is given, which is exponential density with parameter lambda. From this, using the previous stated theorem, from this theorem, we'll find the density function of the transformation or the y. So some more quick examples. So this has not much intersection with the previous theorem. So find p of mod x less than 1 when the PDF, you know what is PDF means. Sometimes you also use these terms: probability density function. So this term we use for continuous random variable. So when the PDF is given by if x is equal to x plus 2 by 18 minus 2 less than x less than 4, 0 elsewhere. Okay, so anyone want to tell me how to do this? Anyone? So how to find the probability of mod x less than 1 when the probability density function is given? Okay, so p of mod x less than 1, this is nothing but p of minus 1 less than x less than 1, which is nothing but f of 1 minus f of minus 1. So this will be minus infinity to 1 fx dx minus minus infinity to minus 1 f of x dx. So this is minus 1 to 1 f of x dx, and this will be minus 1 to 1 x plus 2 by 18 dx. And if you calculate this, you will get equal to 2 upon 9. Okay, another Problem.
Should not it be -2 to 1?
Why -2 to 1?
Sir, because from -2 to -1 it is not 0.
No, but the way I am taking the probability, this is mod x less equal to less than 1, right? So mod x less than 1 means P of minus x minus 1 less than x less than 1. Is this clear?
Okay, sir, I understand. My mistake.
So this is equal to f1 minus f of minus 1. So which is, you see, just we are putting the definition of f1 and f minus 1. So this, the difference of these two integrals, minus infinity to 1 fx dx minus infinity to minus 1 f dx. So this will be minus 1 to 1 integration f of dx. Now another example. So let x have the PDF if x is equal to 2x, if 0 less equal to x less than 1 and equal to 0 elsewhere. So you see here always these two things has to be satisfied, that is fx greater than 0 greater than equal to 0 always. To be, this is a density function, we need fx greater than equal to 0 and minus infinity to infinity f of x here in this case is equal to 0 to 1 2x dx, which you know is equal to 1. Only if these two properties are satisfied, then we say this function is a probability density function. Okay. So in this example, these two properties are satisfied. Now compute the probability that x is at least 3/4, given that x is at least half. So these are the things we have seen before. So this is conditional probability, right? So given that is means x is this probability we have to consider, we have to compute is conditional probability. So we have to compute x greater equal to 3/4, given that x greater equal to half. So which is P x greater equal to 3/4 intersection x greater equal to half, right? This is by definition. So this is by definition by P x greater equal to half. Now this will be, this intersection is nothing but P half is equal to x just once again, I think I made some mistake.
Yes, sir. It should be 3/4 to 1.
Yeah, this should be 3/4. Right? So I made this mistake. So this is P of x greater equal to 3/4 by, probably I copied the problem from the book some wrong way. That's why I convert this x greater equal to half. So this is, now this is 3/4 to 1 f of x dx by half to 1 f of x dx. So I am leaving you to calculate after this. Okay, leaving for you. So we have to do this calculation. Any question till now? The next section, the next topic is what? Which is not of major interest for probability and also for statistics. So we'll see only some definition and some small examples of that. Nothing more than that. No details of no study in details will be done in the topic of mixed random variable. So I hope you can understand what does it mean by mixed random variable. So this is neither discrete, neither continuous. These are the two main random variables which we are studying or will study, discrete and continuous. So this mixed random variable is neither discrete nor continuous, but the mixture of these two things. Okay, so let's see in which cases this type of examples may occur. Let's start with some example. So you see some example. So suppose you have rupees 100 and you have an opportunity to play an A lottery. Suppose you have probability half that you won't play, so you have left with 100 rupees. And you have probability half also the probability half that you play with this 100 rupees you will play and you will win at random some money between 0 and rupees 200. So okay, so you have some 100 rupees you have in your pocket, so you can play or you cannot play. You may play or you may not play. You have probability half that you will not play, then you are left with 100 rupees, and also there is the probability half that you play with this 100 rupees, and then you can win at random some money between 0 and 200. Okay, so this money you are winning, so this is the uniformly distributed. Okay, so anything uniformly you can win, uniformly distributed. Between on 0, 200. Now you tell me, so is this random variable discrete or continuous or nothing or neither? So this is yes.
It seems like both are mixed. Half it's totally discontinuous, and remaining half it's continue.
Right. So this is not discrete because this is uniformly distributed on 0, 200, right? Because if it is discrete, so there are at most countably infinite points you can win. But here you can win anything between 0 and 200, which is uncountable. So that's why this is not discrete. as it takes values between 0 and 200. And why is this not continuous? Can anyone tell me why is this not continuous? As the probability that, so x is the random variable that the money will have. After means if you don't play, then you will have 100 rupees. If you play, whatever money you will have after the play, after the game. That is a random variable. So this is not continuous as p x is equal to 100 has probability greater equal to 1 by half, 1 by 2, right? So continuous means at any point, if you take anything, px is equal to x, it has to be equal to 0. But here px is equal to half 100. So if that is a half probability that if you don't play, and in that case you will get back, you will have only rupees 100, whatever you have before, whatever you had before, rupees 100. That money will still have. So px is equal to 100 has probability get equal to half. So that's why this is not continuous. So this is called, this is a mixed random variable. I hope you have understood this. Any questions? So this we can write this way. Yes,
sir, why is
sir.
it greater than equal to half? Px equal to 100.
Because after the, if you play, so if you don't play, the probability is half. If you play, then you can still have some probability that you will get some money there, right? Okay, you are right. So in the continuous part, will not contribute anything, right? Very good. Thank you. So the continuous part will not contribute anything for the probability at a point. So it is half. It's exactly half. Thank you. So the continuous part will not contribute anything for the probability at this particular point, rupees 100. So its probability is exactly half. Thank you very much.
Why, sir? I mean, that could be at many points that could value. I mean, that can be satisfied.
Yeah, but you know that we have seen that for continuous part, if you take a particular point, the probability is 0, right? If you take a particular point, the probability is 0 for a continuous variable. So this is half is that discrete variable. That is, you are not playing and you are having rupees 100. The other half part is that continuous variable, continuous random variable. And for the continuous part, this px is equal to 100 this is equal to 0 for continuous part. Right? This is because for continuous part. For all x. So px is equal to 100 is also 0. So the only p is equal to x is equal to 100. This comes from the discrete part, which is half.
Okay.
So y is discrete and z is continuous. And we define x to be y with probability p and z with probability 1 minus p. Here p is greater than 0, less than 1. So these things we can define rigorously. So definition is like you are, for this thing you are getting these are the sample space, these are the spaces of all events, and this is the probability space. And for also you are getting the sample space, the space of all events, set of all events, and the probability. So this is the probability spaces, both of this y and z, both of these random variables. Now we define the sample space of x to be sample space of y union sample space of z, and similarly the events of x to be events of y union events of z. You can prove that this is a sigma algebra sigma field. And how we define the, for anything, any x, if you take any event ax, this is ay union az, so this can be considered as disjoint. So this is p into p ay plus 1 minus p into probability of az. Okay. And here, because this is a neither discrete not continuous random variable, so we cannot define the density function.
Sir,
But
we
you
are
can
using
define
plus because, sir, excuse me, sir. We are using
Yes,
plus because they are disjoint, right?
they are
Just to
disjoint. We
cut
will
into
consider this as disjoint. Okay. So this is our definition. So these things are all our definition. Okay. So this sample space is the sample space of this and sample space of this. The events are this union this. Okay. So any event you would take that this is this union this. So this is our definition of a probability of a particular event of x of the mixed random variable p into this plus 1 minus p into this. And this we define this way just because this y and z are disjoint. This way we think this that these two are disjoint. Okay, but this is purely definition of x. When we define the x, we have to define the probability space, means the first the sample space, then the collection of all events, then the probability. So we define all these things. And now the distribution function we define. So this is f of x at x. This is by definition p, this probability of y less equal to small x plus 1 minus p probability of z less equal to small x. So this is nothing but p if y x plus 1 minus p if z x. Okay, any questions? So this will be the end of this topic, mixed random variable. These are not that important, so we'll end this topic here. Any questions you have? Okay, so we'll take some 3-4 minutes break, then we'll come back and we'll start our new section, which is expectation of a random variable. Okay, any questions you have from the last hour? Anything about this transformation of a random variable or mixed random variable? Okay, so we start our new what is called chapter or section probably, which is called expectation of a random variable. So we start with an example, then we'll come to the definition. So the terminology of expectation or the expected value has its origin in game of chance. Again, all these things started with game of chance. So example is that so suppose four small similar chips numbered are placed. So suppose four small similar chips, only difference is that they are numbered. The three have number 1 and one have number 2 are placed in a bowl, and you have to are mixed, and you have to choose one ball randomly, one chip randomly. Okay, so the number is the number on the chip, that is the random variable. So that means suppose you get you draw a chip. If number is 1, number on the chip is 1, you win 100 rupees. Okay, you can think that this 100 rupees as the as the random variable. Okay, so if we draw a chip, that is the event, that is the outcome, and the random variable you are attaching with that outcome is 100 rupees. And if the number on his chip is 2, you win 200 rupees. Okay, so probability of drawing a chip, each chip is 1/4. Each chip is 1/4. So the amount you expect to win, the money you expect to win is 1/4 into 100 plus 1/4 into 100 plus 1/4 into 100 plus 1/4 into 200, and which is 500/4, which is 125. So this amount of money you expect to win in a game. Okay. So more generally, so this will be actually the expectation of this random variable or the expected value. So more generally, Suppose, yeah, again you are playing a game of lottery and you have to pay. You pay rupees A as the game fee, and you can win any number between x1. So these are the random variables. Okay. So this should be the random variables. You can win any number between x1 to xn. So this is game of lottery. You pay rupees A as the fee, and you can win any numbers between x1 to xn. So you have to know whether ultimately you will win more than A. If you win more than A, then you will play this lottery. Otherwise, you will not play. So what is the probability that you will win? What is there any probability that you will win more than A or less than A? What is the probability? If you win more than A, then you will pay. You will play the lottery. And if you win less than A, then you will not play because you have to give rupees A as the fee. You have to give rupees A as the fee. This is. Okay, so this is not capital. Sorry, this is in our sense. In the example I'm giving, these are capital X. These are just small x. And suppose if you just play only once, this is very difficult to say whether you should play this game or not. Because if you play only once, you don't know. In anything you can get in between from x1 to xi. So from that we cannot conclude whether you should play or not. Means you will get more than rupees A or less than rupees A, that you cannot conclude. But if you play large number of times, then what will happen? Suppose you play suppose this number is n. Okay, so after n plays, you give NA, rupees NA, and win. Suppose in the first game you will win capital X1, then capital X2, then capital Xn. Now let n capital N xi be the number of times you win rupees small xi, because ultimately you will win in between from one of this money, one of this amount, x1, x2, xi. So suppose n xi be the number of times you win rupees xi. Okay. So you understand then. So x1 plus xn is then x1 small x1 n x1 plus x2 n x2 plus xr in n of xi. So the average amount which you will receive when, so average amount which you will win is this, which is x1 summation xi n xi by capital N I is equal to 1 to I. Any questions till now? Any of you have any questions? Now, by the relative frequency interpretation of probability, so this is the second definition of probability, if you remember, frequency probability interpretation. So what is that? If you do this, say, large number of times, then this by the total number that will go to the probability, right? With the probability of winning xi, winning the amount xi. So n goes to infinity, so n is large. So this net average amount you win amount of money you win, this is equal to x1 plus x n by n, which is equal to summation xi n xi by n, which is close to xi f of xi. Okay, this is not goes to, this is close to. Okay, this is very much approximated by f of xi. This is close to f of xi. So this amount, which is the net amount, which is supposed to be by this, is you have a chance of actually winning this amount. Summation xi f of xi. So xi varies from 1 to r. So if mu is greater than a, then you should play. So these are the importance of this definition of mu. And if mu is less than a, you should not play, because then you are actually losing some money. Okay, now we are more or less can in the situation to define the expectation. So definition, let x be a discrete random variable. So we first define the expectation, everything for the discrete random variable, then we'll go to the continuous random variable. So let x be a discrete random variable that assumes a finite number of values. This is our first definition. Okay. So here this assumes only finite number of values. x1, x2 to xr with density f. So this has the density f, this is a discrete random variable. Then the expectation of x which we denote by ex is defined by summation xi f of xi is equal to 1 to r. Okay, so some example. Suppose x has, so this is the discrete case. The uniform distribution, so this is discrete uniform density on x1 is to xr. So that means each of these thing has the same probability, which is 1 by r. There are r number of things, and we pick anything. So this has the randomly we are picking anything. So this has the same probability. Each of these has the same probability 1 by r. So then E of x is equal to x1 by r plus xr by r, which is the arithmetic average of the possible values of x. So see, each of these xi have the coefficient 1 by r, right? Now in the previous case, this is the coefficient f of xi, and here particular case, this each of them has the coefficient 1 by r. So this is so one remark. So ex is called the mean of x. The mean of x, and which is denoted by mu. So you also denote ex by mu, or you also say the mean of the density of x, f of x, or mean of density of density f of x. And yeah, there's something. Okay, and in general, what you see here, this is summation summation xi f of xi. So in general, ex is a weighted average of the possible values of x. Because we are attaching the weight f of xi. And also you see that the density is actually at each point or at some interval or something, we are defining some number. So by Ex, we are actually trying to represent, or what is the better way to say this? We want to summarize a probability distribution by a single number, that is the Ex. Okay, so before we are having some random variable for here, we have the distribution function. So these are a density function. Density function is defined for all the values, all the possible values of all real numbers. Probably the density function is defined. But here Ex, by Ex, we are actually trying to summarize the whole probability distribution by just only one number, which is the expected value of that random variable or the expectation or the mean, by which we are trying to summarize the whole probability by just a single number. But we don't know whether this is a really good way to summarize the probability or not. So this depends upon this is a good way. Then actually the distribution is very much clustered about the value mu. Okay, it's very much close to the all the distribution is very much close to the mean value mu, which is the mean or the expectation. But if it is not near the mu, then this Ex is not a very good way to summarize the probability distribution. If it is near mu, if all the values are near mu, then this is a good way. We can summarize, we can represent the probability distribution by a single number, which is the mean. Otherwise, this is not a good way to. Otherwise, this is not a good way to represent. Okay, any questions? Okay, now the second example will come. So binomial distribution you have seen before. So this is the probability of you are just tossing a coin, head or tail. Suppose head has this may be a biased or unbiased coin. So suppose the head has probability p and tail has probability 1 minus p. This we also can show as, instead in place of head and tail, we can also say as failure, success and failure. Success has probability p and failure has probability 1 minus p. So you do the same thing in many times. So how many head you will get in n trials? How many head you will get, or in n trials, how many successes you will see, you will face. This is the binomial random variable which we defined before. So for this, we will try to calculate the Ex. So case 1 is n equal to 1. In this case, X assumes the values 0 with probability 1 minus p. So 0 means tail or 0 means failure, and 1 with probability p. So here expected value, expectation is 0 into 1 minus p plus 1 into p, which is p. Now we do this for any n. So here what is the expectation is summation j. So j is equal to, so there may not be any, if you're doing n trials, so there may be no hit or no success, or maybe at most n successes. So 0 to n, the xi is this xi. So what is this? This is just xi f of xi. Now in our case, xi is just j, and p x is equal to j, and px is equal to j we did before. So this is, these things are very easy. So I'm just doing little quickly. In choose j, this p of x is equal to j is in choose j, p power j 1 minus p power n minus j. So these things was done before in the class. So here j into n minus j is j into n factorial by j factorial n minus j factorial, which you can do more things, and you can write as n minus 1 choose j minus 1. So ex you can write as, you can take this n out and some p out from here. Np j is equal to z to n minus 1 choose j minus 1 p power j minus 1 and 1 minus p power n minus j. Now put j I is equal to j minus 1. So this is equal to np summation I is equal to 1 to 0 to n minus 1, I think. Yes, n minus 1 choose I, p power I 1 minus p power I, n minus I minus 1. Okay, n minus 1 minus I. Okay, now this part is actually equal to p plus 1 minus p. This is just a binomial expansion for n minus 1 is equal to 1. So this will be just np. Okay, I have done it little quickly, but the things you can see very easily, and this will be np. Any question till now? Anyone have any questions? Ashish Kumar, do you have any questions? Ashok Jangir, do you have any
Yes, sir.
questions? Do you have any
Sir,
questions? Yes, sir. Tell me.
sir, one little question is that when we are talking about the expectation, then n should be anyhow a limited number, right?
No. Till now we have defined only for the finitely many values. After that, we will define for infinitely many values. I am coming to that now. Okay.
Okay, sir.
So this is
Okay,
any discrete random variable. So the x can assume the values both finite and countably infinite.
Okay.
Okay. This question I do now. This definition. So suppose x is any discrete random variable with possible values x1, x2, xr. This goes on. It can be finite or countably infinite. Then how should we define? We should define the expectation to be ex summation xi f of xi, right? But the problem is whether this infinite sum, whether this converges or not, whether this is finite or not. Okay, this may or may not converge. So for that, what is do? So if summation mod of xj, because xj we don't know whether xj is finite or is positive, negative, zero. Xj can be anything. But f of xj is f of xi. It's right. I right. So we don't know whether xi is positive or negative, but f of xi is always positive. If f of xi is finite, then we say that x has finite expectation. And we define its expectation to be summation xi f of x. So you see, because this is finite, that's why this summation also converges. Okay, so this infinite sum also converges because this sum is finite. Otherwise, if this summation is infinite, then we say x does not have finite expectation. And ex is undefined. Okay. So Jamil, the confusion you had, is this clarified now?
Yes, yes.
So yes,
all these will
yes.
be possible if term will be the, I mean, exponentially decreasing term. So anyhow, that will be if will definitely get a finance.
Can you repeat your question? I didn't get it.
No. I was just saying that for that xi is in such a manner that that value will be decreasing exponentially, so that that should not go into infinite if that exists in case of finite, right?
Right. So we don't say exponentially, yes, but it will decrease in such a way that the infinite sum will be less than finite. Is less than infinite, or infinite?
Yes.
Infinite sum is actually finite. Okay, now so in all the cases, this is not possible for us to compute the expectation. So what we do, we actually use some tool, right? So some theorems are there, or some formulas are there. We use those as tool to compute the expectations of various random variables. So these tools we write as a theorem. So this theorem comes here. Let x and y be two random variables with having finite expectations. So we are doing this theorem 2 because there is one theorem 1 which will come after this. We'll first state all this theorem. Then how to prove this theorem? For that we'll state theorem 1. So having finite expectations So if C is constant, and Px is equal to C is equal to 1, then Ex is equal to C. Second is, if C is a constant, then Cx has, so this is another random variable, Cx has a finite expectation and the exponential of Cx is equal to C of exponential of x. Sorry, the expectation of Cx is equal to C of expectation of x. So both x and y has a finite expectation. So x plus y has finite expectation. And ex plus y equal to ex plus ey. P x greater equal to y is equal to 1 implies the expectation of x is greater equal to expectation of y. Moreover, ex equal to means if this is true that p x greater equal to y is equal to 1, then ex is equal to ey if and only if p x is equal to y is equal to 1, and is x has finite expectation if and only if, so this is if and only if, okay, so this means if and only if, which we write as if mod x has finite expectation and mod of ex is less equal to e of mod of x, expectation of mod of x. So we here prove 1, C and A, C and E. So to prove A and C is not difficult, but to prove A and E are not difficult, but to prove C we need some other theorem, which is theorem 1. So A is given x is equal to C is 1. So x not equal to C, then P of x is equal to small x is equal to 0, right? As so, is this okay that if x not equal to C, then probability of capital X is equal to small x is equal to 0, because capital X is equal to C has probability 1. Okay, if you don't do the if you can at present, if you can't do this rigorously, you can do on your own. This is not difficult. So Ex is equal to summation x fx, which is C into fc, which is C into p x is equal to C, which is C into 1 equal to C. Now we go to E. X has finite expectation if and only if summation mod xi, if of xi is less than finite, if and only if summation I double mod you are taking, means double mod is same as single mod, but okay, for the next thing I'm doing this, if of xi is finite, and this implies mod of x has finite expectation. So x has finite expectation implies and implied by mod of x has finite expectation. Okay, and what is ex? Mod of ex is equal to mod summation xi f of xi, which is less equal to, you know, that mod of xi f of xi, which is expectation of mod x. Okay, any questions? Now we'll prove theorem C. It is if x plus y has finite expectation and e of x plus y, then if x and y have finite expectations, then x plus y has again finite expectation, and e of x plus y is equal to x plus ey. So to prove this, we need some more thing, which is called discrete random vector and joint density. So these things actually will you'll learn later. I am just giving the definitions, but not in details. I'm doing later. We'll go these things in details. So this is discrete random vector and joint density. So that means if two random variables are there, how can you get a random variable using both these two random variables? So this is again, we start with sample space, the collection of events, and the probability. So probability space, this is a discrete r-dimensional random vector x is a function x from this species of the sample space or the species of outcomes to r power r. So previously you were taking the r, the real numbers. Here you are taking r power smaller. Okay, nothing else. Everything else is the same. Taking on a, so this is just a, previously you are taking discrete random variable. Here you are taking, that is a map from r to r. So discrete random variable is a map from omega to r. Here you are taking r power r. So this is a discrete r-dimensional random vector. So previously it was discrete random variable. Such that taking on, so again this will take either finite or countably infinite values. Infinite values. So these are elements of r power r. So I am writing this way. Such that omega x omega equal to xi, this thing is an event. Just the definition, just like the definition of discrete random variable. There it was mapped from r, omega to r, here omega to r power r. So here we define also the density function f of x1 is to xr. We define as again p x1 x2 xr equal to x1 x2 xr, which is nothing but p x1 equal to x1 x2 equal to x2, this way xr equal to small xr. So now this is one connection between discrete random variable and discrete random vector. If x1 x2 xr are dimensional are random variables, then this is a new random variable we are defining, which is by definition x1 omega up to xr omega. So this is a discrete r dimensional random vector, and here the density function, this is called the joint density of x1 is to xn. I know this is a little bit difficult for you to understand all these things, but yeah, when you see these things details, then this will be clear, I hope. So, but to prove these theorems to see, we need all these things. Let phi be, yeah, I know, but only 2-3 minutes will take. Let phi, only this last thing I will write. Phi be any real valued function defined on, okay, write this on R, then summation x, okay, we'll do this thing in details in tomorrow's class. This is by definition, this is our notation, just nothing else. I phi of xi bar, f of xi bar. Okay, so from tomorrow's class, we will start after this in tomorrow's class. And this week I want to take one extra class, maybe Friday evening after 5 or Saturday. So do you have any class on Friday from 5 o'clock?
On Friday,
Yes.
sir, we have a lab till 5 and submission till 9:30. So Friday is not a good option for at least civil engineers.
On Thursday?
So on Monday, Thursday, and Friday, we have an HSS from 5 to 6.
Okay, then Wednesday, if I can, maybe I will inform tomorrow. Wednesday from 5 to 6, I will take one extra class. Okay? I will
No,
inform
sir,
you tomorrow.
not Wednesday,
So
sir.
Wednesday
Sir,
we have lab.
Okay, then Saturday, the only option.
Yes, sir.
Okay,
Okay.
Saturday, the time I will tell you later. Tomorrow, I will
Okay,
tell
sir.
the time of Saturday. Okay, so any questions you have, others can leave. If you have any questions, then you can ask, others can leave. No questions? Okay, so we stop today.
Sir, when Saturday?